Okay. Hello everyone. Thanks for joining us today for our conversation on how green chemistry and sustainability is advancing soy innovations and driving sustainable solutions. This webinar will highlight emerging technologies, the role of soy in these technologies, and how educators can bring these innovations into their classrooms. I definitely encourage you all to post your questions in the chat. And today we have four wonderful speakers who will be speaking to soy innovations and applications in industry, as well as educators trying to use those innovations as curriculum materials to support teaching students about the importance of green chemistry and sustainability. And so with that, I will pass the mic to our first speaker, Chris. Chris, please take it away. Thank you.
Well, thank you, Monica, for the introduction. I'm Chris Weigel from OmniTech International, and with me today I have Rick Heggs, so we'll be sharing this presentation. So welcome to Moving to Renewable Feedstocks, Soy Research and Innovation. So just a little bit about this webinar and our webinar series. This is going to be the first of many that we plan on doing, and this is all supported by the United Soybean Board. Thanks to their generous financial support, we're working in collaboration with Beyond Benign to really educate and inspire educators and the rest of the technical community to look at soy for feedstocks, for materials from coatings to lubricants and a number of other industrial applications. So what we're going to do is showcase some soy-based innovations and also, more importantly, some commercially available soy-based products. Our goal is to raise that awareness of what soy's role is in industrial applications and sustainability. It's just not for food, fuel, or feed. There's many industrial applications we're going to be showcasing today. So we just ask that you join us to explore, look at some of these cutting edge developments in soy, and really consider soy as one of the renewable feedstocks as you do industrial applications. So from here, I'm going to pass it on, and we're going to watch a very nice video that will really inspire you to consider soy for industrial applications.
It's time to talk about us. Not him, not her, not them. Us. Grab a seat. Thanks to us, things have been great. In fact, you can find us just about everywhere. Your food, that's us. Your food's food, that's us too. Your fuel, that's us. That toy she's holding, us. That treat he's inhaling, oh, that's us. Slow down, big guy. That's us too. Oh wow, that is so you, but it's also us. Us. Definitely us. Us. Definitely not us. Us. Wait, back up. That's us too? Polly? Really? Us? Wow, okay, Polly says that's us too. Victory Lane? That's us. Seventh inning stretch? That's us. 4th of July? Definitely us. So don't get too comfortable. These opportunities and possibilities won't stop anytime soon, so how far our nation's soy can go is up to us. And should anyone out there happen to doubt us, by all means, just watch us.
Okay, I hope everybody enjoyed that video. It's very exciting to see, and this is just a very small sampling of some of the industrial applications for soy. So many of you might be asking, why should we consider soy in industrial applications? Well, first of all, as Rick will be soon presenting, U.S. soy is certified as sustainable. It's a great renewable alternative to the petrol-based feedstocks. Many of us are motivated to reduce our environmental impact, but yet you're not sacrificing performance. The applications are endless. There's versatile applications among many industries. Soy in itself is generally regarded as safe. It's biodegradable, and also it enables chemistries for improved environmental health and safety. It's high in quality, especially US soy is known to be the highest quality of any soy that is grown around the world. It's abundantly available. It's very economical, and it's grown right here in the US. And especially in light of the recent transactions that are going on with the global trading, this is very exciting as we'd like to take our own feedstocks in from our own countries and consider them for our future development. At this point, I'm going to be turning it over to Rick, and he's going to be talking a little bit more about United Soybean Board and the sustainability of soy.
Thank you, Chris. So who is the United Soybean Board? The United Soybean Board is an organization that is funded by the 515,000 plus U.S. soybean producers in the United States. The board consists of 77 farmer directors from all of the soybean growing states, and the board is chartered to promote the sustainability of U.S. soy farmer. The budget supports research, promotion, and investment to develop demand and also to increase the supply of soybean as we go forward. When we say a checkoff program, it means that 1/2 of 1% of the net market value of each bushel sold. So the first sale of the bushel, 1/2 of 1% goes into the checkoff, and that money is then split between the states that are growing soy, and then also 1/2 of it goes to the national organization, which is the United Soybean Board. Um, so the most recent budget was approved. It was $173 million. So it's quite a substantial amount of money to promote soy and increase the value of soy to the farmers. Next slide, please. So we talk about soy being a sustainable feedstock, and we don't just say that. We have data and evidence to back that up, and we'll go over some of that in the next few slides. So this is the framework where we're looking at how are the metrics that we claim sustainability for, and that goes all the way from water management, nutrient management, innovations in plant breeding to increase yield and increase resistance to pests. There's different types of farming that can be used to conserve the soil. Cover crops during the winter also improve the quality of the soil. Reducing runoff into streams and ponds and lakes by having these buffer zones, buffer strips around water and around the fields. So let's go to the next slide and we'll talk a little bit in more detail on how this is actually administered. So there's something that we call the U.S. Soy Sustainability Assurance Protocol, and that's a third-party audited program. More than 90%, in fact, I think around 95% of the soybean farmers in America have signed on voluntarily to grow soy under this protocol. There's 4 sustainability directives, and this has been looked at and approved by a number of global organizations that look to determine whether something is sustainable or not. Some of them are in Europe, some in Asia, and some here in the United States. So it's been well founded in data, and all of these organizations agree that soy is a very sustainable crop. These are some of the metrics which are used in the last 40 years, from 1980 to 2020. Soy has gone to produce the crop with 46% less energy, 43% less CO2 emissions per bushel, water use and irrigated water, 60% less irrigated water per bushel, more efficient land use, and soil conservation improvement, 34% less per acre. So that's the history. As we go forward, there's the new goal for 2025, where we want to reduce the land use impact by an additional 10%. Soil erosion by 25%. We do this through cover crops, through no-till farming where we don't have to plow the fields, increase energy efficiency, and reduce total greenhouse gas emissions by 10%. So we have aggressive goals going forward, and we want to make sure that soy is the #1 sustainable agricultural crop in the world. Next slide, please. So we've also looked at in some detail, not just growing the crop, but also processing the crop. And we did a life cycle analysis funded by the United Soybean Board, which was published in January 2024. Next slide, please. So up at the top of this slide, you can see that farmers to grain elevators, sort of the path that the commodity takes for storage. But after it gets into storage, then it must be processed into the products which are used by industry as well as by agricultural feed and U.S. Human consumption. So it goes from the bean through a number of processing steps to a meal product, the primary product. There's a protein product, which are a lot of the food uses, both for human and animals, and then also an oil product, which has a fuel use, it has a food use, and it also has an industrial use. So this is the system which was looked at for this life cycle analysis. Next slide, please. So focusing on global warming potential, since 2015, when the last LCA was done, to 2024, 19% reduction in global warming potential gases per kilogram of soybeans, 6% per kilogram of the meal, and 22% per kilogram of the crude soy oil, and 8% per kilogram of the refined soy oil. So this data was pulled from 454 farms in 16 different states. And we also had 52 soybean processors. Those are the people that turn the soybean into the meal and the oil, and 27 oil refiners, which take the crude oil and make the refined oil. So it's a quite a broad-based look at the industry across many different farms, many different processors, and developing this data showing that not only is soy sustainable, we are aggressive in trying to make it more sustainable as we go forward. Next slide. So Chris mentioned the fact that soy is an abundant crop and it's a global product. So, if you have a multinational company that's developing a product, they don't have to worry about a feedstock not being available in certain parts of the world. So this chart shows who grows soy around the world and how much they grow. So Brazil is the #1 producer of soy currently. The United States is #2, and Argentina is #3, along with a number of other countries in Asia and Europe. All over the world, soy is produced. And it's produced in vast quantities. As you can see, the 10-year average between 2015 and 2024 was over 350 million metric tons. So that's a huge amount of material. It's available for multiplicity of uses, food, fuel, feed, food. The message here is that soy is very abundant, and it's available to do all the necessary production for any type of product. So just in the US, drilling down on that, you can see that we've got about 267 billion pounds of soybeans annually. And after being processed, that corresponds to 28.6 billion pounds of soybean oil and 113.9 billion pounds of meal. So again, the meal is the protein part. The oil is the part that's used for many different industrial products to replace petrochemical oil. And there's plenty of it. there's plenty of it. So it's a very abundant and globally available material. Chris, are you going to do this? Or do you want me to continue?
Go ahead.
Okay. So this is, I mentioned that there's a number of processing steps to go from the bean to the various products. And this is sort of a very simplified version of that. So the soybeans are first cleaned, what they call cracked or crushed and dehulled. So there's a skin on the outside of the soybean, which is called the hull. So that's the first product that comes off. It's a fairly low value product, but a lot of people are looking at the hulls for certain types of industrial products because it is very economical. That results in a soy chip, what they call a soy chip, which is conditioned and flaked, which is basically again compressed into from a chip to a flake. It contains the oil and the meal. That's why it's called a full fat flake. The full fat flake is then extracted with solvent to extract the oil and remove it from the meal. And then you have the two main products, the oil and the edible defatted flakes, which then go on to make soy meal.
Okay, well, thanks, Rick. Thanks for giving us that background on sustainability. That's something that the farmers are so incredibly proud of. So I'd like to go into now the soybean. A lot of us look at the soybean fields in the area and we think of food. And a lot of us are questioning or may get the question about how we compete against food versus the fuel and the chemicals. Well, this explains a lot of it. First of all, as we mentioned, soybean is grown predominantly for the meal. And of that meal, it's about 80% meal, 20% oil. The meal, about 96.6% goes into animal feed for predominantly swine and for poultry. Only about 2.5% goes into human consumption, and that might be our soy milk and our tofu and so forth. 0.5% into aquaculture, and only about 0.3% into industrial applications, which we'll talk a little bit more about in the slides to come. Now, on the oil side, which is predominantly what feeds into fuel and most of our industrial applications, about 48% of it goes into human consumption. So if you call this food, well, it's mostly to fry our French fries and probably, a lot of the fried foods that we see today. 41% goes into fuel, and only about 9.5% or 6% goes into industrial applications. That's where we're focused. So you see that we're not taking food off the table. We're not really competing. Still, a large percent of it goes into the food. We are just kind of taking up the excess here when it comes to soy. So let's drill a little bit more into the chemistry, which a lot of us are motivated to see today. So on the left-hand side, we have the structure for soybean oil. Other building blocks that can also be used to really, help us with chemistry and reactivity are epoxidized soybean oil, which many of us have heard of that many times over. That improves the functionality so we can look at other chemistries, to make soy polyols and other resins and building blocks. Methyl which is popularly used as a solvent in itself to replace petrol-based solvents, and then epoxidized methyl. So let's dive into where some of these building blocks are used in industrial applications. For many years, we've had paint and coatings. In fact, those applications have been around for probably close to 80 or even 100 years. There's other ones including infrastructure, which includes concrete and asphalt, adhesives, lubricants, rubber, such as our tires, polyurethanes, many cleaners, and personal care. And we're going to drill into these a little bit more detail. We'll show you some of these commercial applications that you might have not known about. And hopefully this will inspire you to think about some applications that you'd like to get involved in for the development of soy. The first one is coatings. And as I mentioned, soy's been used in coatings for probably 80 to maybe even close to 100 years. This really started with alkyd resins. In fact, I think Rust-Oleum has now been in business 100 years, and they're one of the leaders in alkyd-based wood coatings. So these alkyd resins and alkyd acrylic hybrids and alkyd dispersions can go into a multitude of both exterior and interior paints, coatings, and stains and primers. But there's other applications, including powder coating resins, concrete stains, concrete sealers, asphalt coatings, and even traffic marking paint. On the right-hand side, you see the logos of the companies that have commercial products that are made with soy today. The next application is asphalt, and this is something you never think about when you see your asphalt roads being paved out there. But this can go into a number of different applications in asphalt. You know, first of all, there's release agents, cleaners in themselves. There's been companies such as Soleil that have developed thermoplastic elastomers to assist the asphalt from having a very consistent high and low temperature performance. There's seal coatings and striping, emulsifiers, even pavement fog sealers that you spray on top of a pavement to extend the longevity of tired, old, cracked asphalt. And then solvent cutbacks and even flux oils, which are the oils that are used to help with asphalt, you know, to make it more pliable and help with the application. So again, on the right-hand side, you see some of the companies that have developed commercial products in this area. Roof rejuvenators, I spoke about fog sealers. Well, roof rejuvenators work the same way. Many of you have probably seen the Roof Max commercials on TV. This is, again, based on soy, and it's used to, you know, just rejuvenate the poor, tired asphalt that is cracking on the roof of your home and rejuvenate it and give it another life. Concrete. This is another area where soy is used in everything from durability enhancers, protective sealants, and other barrier coatings and stains, the release agents, and a lot of cleaners and seal removers and, you know, concrete cleaners and so forth. Again, many applications out there that are now commercial. Wood adhesives, and as I mentioned a few slides ago, there's not many applications that are based on industrial applications on meal. And this is one exception where meal is used in wood adhesives. It's the protein that is able to cross-link with other materials to provide a very strong adhesive binding in engineered hardwood plywood and other types of engineered wood applications. And this is something that replaces a lot of your formaldehyde-based adhesives, which makes it much safer, not only for the manufacturer, but for the installer and the homeowner. Then there's other adhesives, and this could be anything from floor covering adhesives, insulations, adhesives, anything that binds wood together or packaging or labels, and even adhesive removers, which are mostly the soy methyl ester solvents that are used for removers. These are all, again, commercial products that are out there with soy. Lubricants is very popular. In fact, vegetable oils have been used in lubricants for actually centuries. So soy is no exception. And the application of soy in lubricants is great because soy is safe. It's great for environmentally acceptable lubricants, or there's total loss applications. There's many applications of lubricants, and you see, again, some of the more exciting applications are here. In fact, a more recent one has been DeWalt. They have launched a line and have a strong, you know, sustainability initiative. and using soy in their lubricants. And it goes on to many other applications, as you can see on this slide. Rubber and plastics, probably the greatest one here are tires. Goodyear has now launched 11 tire lines that contain soy. So if you Google Goodyear and soy, you'll be overwhelmed by the number of models that they have launched with soy. But also that same technology is used in our Skechers shoes. So from what I understand, every pair of Skechers shoes contains soy using that same technology. But generally, soy is just a very good process oil for rubber and can be used in a number of applications. Another application would be the epoxidized soybean oil in itself that can be used as a secondary plasticizer in these types of applications. Then there's polyurethanes. Soy polyols are used in polyurethanes. Huntsman is probably one of the largest in this area. They have a soy polyol that's used for spray foam insulation. But then you see other applications out there that go into window profiles and countertops and carpet backing and sun lawn artificial turf. So there's a number of applications for soy in these types of applications. And then the second to last are the solvents in themselves. And again, this is predominantly the soy methyl ester, but it could be derivatives. And the applications here are endless, anywhere from laundry to household or industrial cleaners, graffiti removers, paint strippers, ink removers, and even hand cleaners. And the last application is in personal care. Now, this doesn't move the needle as far as volume is concerned, but personal care industry takes soy very, very serious, and it's used in anything from body washes and shampoos to conditioners and skin and hair care. This is one that even hydrolyzed soy protein can be used in for conditioning for hair products. So in summary, why soy? Well, first of all, we are all focused on improving performance, and we can indeed do this with US soy. First of all, because it's very sustainable. As you can see, it enhances a number of different chemistry and has diverse applications. It is indeed economical, very consistent and high in quality. In fact, people around the globe talk about US soy being the highest of quality of any grown, and then it's abundant in supply. And with that, I'd like to turn it over to Jane. Thank you so much for your time. And at this point, we're going to move on to the staff at Beyond Benign.
Oh, Jane, you're muted.
Yes, I'm unmuting. Okay, can you see my slides?
Yes.
Yes, okay, great. Hi, everybody. So thank you so much for joining us. My name is Jane Wissinger. I'm Professor Emerita from the University of Minnesota. And passionate about green chemistry curriculum. So I am so excited to be part of this project supported by the US board. And our goal is to take all those amazing applications that you heard about. I've just learned so much about where soy is and have a new appreciation for the versatility. And now what I want to do with my colleague, Michael Wenzel and Beyond Benign, is to bring those innovations into the classroom. So we're going to design a versatile, easy, adaptable chemistry curriculum that highlights soy as a renewable feedstock, a lot of replacement for fossil fuels, incorporating green and sustainable chemistry, and bring awareness to this very important crop. So our team is Amy Cannon, Director of Beyond Benign, and Monica, Content Manager, who formed this collaboration with US Soy and Omnitech, and myself and Michael Wenzel you'll be hearing about from very soon. All right, I'm going to pull up my pointer so I can point. All right, laser pointer. All right. So our plans for the curriculum are this, starting with the structure and level. First of all, it will be open access to everybody, tailored mostly for higher education, but I see potential for upper levels of high school. Very flexible, so we're going to build it so that instructors can pick and choose what they want to include in their curriculum and what courses. I'll be sharing with you a variety of courses. Has to meet education standards, so both the bachelor requirements here in the United States and next generation standards. And if it doesn't connect to chemistry, instructors aren't going to use it. So we're definitely going to build in and model the connections to chemistry concepts that are regularly taught, just incorporate that excitement with real world commercial applications of a renewable feedstock and highlight the green and sustainable chemistry. For the instructors, what we want to do is, I'm not sure if you're seeing the screen, is first up, building a module that has history, background, the chemistry that again is the instructors can select from. Then we're going to model all the wonderful applications that Chris shared with industrial case studies. And we're just going to tease you a little bit with 2 today, and I hope in future webinars we'll be sharing more to get your interest. And then look at modeling through laboratory curriculum as well. So of course we want to have the use state-of-the-art teaching pedagogies with student activities and projects, spell out the learning outcomes, and again, just get students excited about real-world applications as soybeans as a renewable feedstock. So in Module 1, just a little bit here. History is always something subjective that instructors do like to or not incorporate when they're teaching, but we're going to have the very interesting and long history of the soybean related to human culture going back 3,000 years. It is old, mostly in China and Asia, and then through opening up the world, getting over to Europe in 1737 with the Netherlands. The US history is very interesting in itself, coming to Savannah, Georgia by Samuel Bowen in 1765. And then moving around the United States to where a lot of the soybean is grown today in the Corn Belt. We have a farmland in South Dakota that we have a farmer farm that has lots of soybeans on it. If anything else, one very interesting tidbit of the history is this collaboration between George Washington Carver, an agricultural scientist, and Henry Ford, who was building cars, and their idea that these 2 industries should be connected. And Ford has, built this soybean-based car. They used lots of parts that plastic designed from soybeans. So that's really fun fact to share with students. And so there's going to be this history and the current status that was shared of the soybean industry by Chris and Rick. What about the sustainability attributes? Again, what we're highlighting is green chemistry principle number 7, renewable feedstock, replacing depleting resource that is fossil fuels. So you could see many of the applications Chris shared were could have been fossil fuel based, and we're looking for replacement for it. Other green principles will automatically come around with that. I've been very impressed with the whole efforts of the soybean industry to address sustainability in all the different aspects, looking for preventing waste, considering the life cycle analysis, using benign chemicals, designing benign chemicals. There's solvents designed from or made from soybean. And then many renewable feedstocks have the ability to be degraded through natural enzymes and organisms. So all great things that will be tied into the curriculum to get that green and sustainable chemistry in. And if you're interested, as I am, of incorporating the UN Sustainable Development Goals, Rick shared all the aspects of sustainable farming that the industry, the US soy, is interested in incorporating. Of course, we're talking about how can we use sustainable food production systems to combat hunger, clean water using the sustainable farming practices that were shown. Fun fact is soybeans are a legume, and so they don't need as much fertilizers as many of the other seed oils. So I really like that fact. Achieving environmentally sound management of chemicals, if you can use less pesticides, fertilizers, you're going to increase the sustainability efforts. And then climate action, of course, was also shared in the slide by Rick, and life on land, conservation, restoration of the land, all in sustainable farming practices. So what courses are we hoping you'll take a look at that can incorporate this soybean curriculum? Of course, general organic foundational courses, just as we talk about the molecules, it's on the next slide. You have considering the molecular mass, intermolecular forces, the functionality, the reactivity, and thermodynamics, if we're going to talk about soybean as the fuels. The biochemistry, I'm going to show you some of the cool carbohydrate and protein structures if you're teaching a biochemistry oriented course. There's many are teaching analytical or food science courses. We have food science majors in Minnesota that this is great, will be great curriculum to incorporate with the composition. And polymers materials, Michael and I have worked a lot with getting curriculum that incorporates green sustainable chemistry through looking at really fun polymers. So we're going to share, Michael's going to share some activity in that area. And of course, upper division environmental sustainability green chemistry courses. So molecules, we're chemists, triglycerides, as Chris showed you, this is the structure. I like sometimes to make it in this fancy nonlinear form. Carbohydrates are part of the meal. So of course, this is the soybean oil with the triglycerides. In carbohydrate structures, soy meal has both sucrose and cellulose type molecules in it. In the meal also are these protein structures to talk about peptide bonds, etc. And then little niche where we want to investigate is lecithin. This is such a cool molecule. It's got everything, charges, phosphorus, nitrogen. So looking to see what's happening in that realm with innovations from soybean, those doing soybean research. Chris talked about the triglycerides, but just putting it in the context of curriculum, of course, we can talk about the 16 and 18 carbon chains with the all cis double bonds and the reactivity. So as I mentioned, we will build in student activities where students would identify the functional groups present, what bonds are susceptible to what kind of reactions. Allylic, I found students always had trouble with. What's that allylic position? That's where a lot of reactivity can take place with double bond chemistry. So we'll be building these lessons for instructors, for students. The properties, why is it that soybean oil, and I'm going to show you an example, is so uniquely fit for a lot of these applications. So you can think about the water solubility, the density, and of course, highlighted in green and sustainable chemistry is the low or no toxicity, as Chris mentioned, generally recognized as safe molecules. Lots of reactions can be done with soybean oil. One really interesting one to bring up is the reaction with iodine, and a classic characterization of seed oil and vegetable oil is looking at the reactivity with this iodine and characterizing the number of double bonds, etc. So great content to bring into students and an exploration for them to do. So that's some of the background we're going to include in the curriculum, and now we're ready to dive into looking at some applications. So as I said, just some teasers. I'm going to show you a really successful older application as a case study, and then Michael's going to show you a really new emerging one. So case studies. And at this point, what I want to say is if any of you are really interested in seeing a particular case study from the many applications Chris shared, please contact us. I'll put my email in the chat to let me know what you might be interested in. So there's a lot on this slide, but a very successful application of soybean oil has been in transformer fluids. So of course, transformers are everywhere. It's how electricity, efficiency, the power is sent increase and decreasing voltage. So they need an insulator that can withstand high temperatures. And at first, mineral oil was used, but this resulted in the fact a lot of fires and then spilling of the mineral oil, which is not degradable, and environmental harm. So PCBs were developed, polychlorinated biphenyls. And of course, what we know now is though they were a better alternative for mineral oil, they are not a better alternative for the environment. PCBs are in the same class as some of the chlorinated pesticides. They're persistent organic pollutants, have long half-lives in the environment, and are now known to be endocrine disruptors. So soybean to the rescue. So Cargill Incorporated won a Green Chemistry Challenge Award for inventing a transformer fluid derived from soybean oil. So anytime you have something related to the Green Chemistry Challenge Awards, I really encourage you to have your students look at all the awards that are in there and get excited about new technologies. And you could search for soybean vegetable oil related, and there are lots of them. But this was very successful in replacing the PCBs and mineral oil, and better than mineral oil and higher capacity, 0 fires in all the years. And if it does spill, even in transportation to the transformers, etc., 100% biodegradable in 10 days. Hooray. All right, Michael.
Hello, folks. My name is Michael Wenzel. I'm at Augsburg University in Minneapolis, where I'm the chair of the chemistry department and professor. And I'm also part of the team here to learn more or to help spread the word about soy. And I think one of the neatest things is I think this is a large industry, and I think as educators, we're trying to train students to be successful. And I think this is an opportunity for students to learn about this, but also work in this. There's a large career opportunities here as well. Really inspired by a lot of the work in academia and also in industry of folks that have been funded by this, the US Soybean Board. It's one of those things is this idea about adhesives. And I guess we don't always think about adhesives, but they're kind of present all the time in our everyday lives. And they're really interesting things for students to think about as we kind of come back to thinking about those core chemical principles students be learning about in classes, right? Students learn a lot about intermolecular forces, hydrogen bonding, covalent bonding. Maybe in higher level classes, they might learn about amorphous or semi-crystalline polymers. And then especially the concepts like TM and TG, right? When we think about adhesives, what kind of physical properties do they need? I think they're found all over the place, and there's different things that students need to think about for those. And most of the time, adhesives are petroleum sourced. So can we think about using soy as these alternatives? And then these kind of like questions for students to think about. We've been kind of adding these in with these case studies, and what kind of properties of adhesives would you want? What are kind of examples? And then what makes something sustainable? And looking to highlight different cutting edge research that's, Nature papers from 2023 from the Wilker Group at University of Purdue is really interesting ways to do that and highlight those things and kind of give context for students when they're learning these things. If you're going to learn about hydrogen bonding, if you're going to learn about covalent bonding or intermolecular forces, let's give them some context and some things in everyday life. And then also with the sustainable feedstocks such as soy. So go ahead, Jane. So one of those cool things I think is to think about as we're thinking about renewable things and how do chemists, how do chemists approach problems? How do we solve problems? What if you can look at nature and natural adhesives? So this group actually looked at mussels, which are underwater, and right, they obviously have some sort of adhesive properties. And how do you take those ideas of biomimicry and then apply them as chemists would use them? And so what these folks have done, they took epoxidized soybean oil, which was mentioned as a high feedstock that's easily readily available, and they took the inspiration from mussels, which use catechol, so the phenolic OHs, and they use tannic acid, which has a similar thing but is also renewable, and malic acid, and doing a type of cross-linking with epoxidized soybean oil with these two cross-linkers. They were able to make really strong adhesives that are actually adhesives underwater too, which is something, again, that's not necessarily possible with most adhesives. So it's pretty neat to see this kind of what chemists do. Like students can see what chemists do and how they take inspiration from nature, but also using renewable feedstocks as both the polymers, the epoxidized soybean oil, and the cross-linkers too. It's just really exciting things to think about what's possible as you go forward. So this is one of the first case studies on adhesives we wanted to do. And so this is kind of a three-pronged approach. So we kind of had Jane introduce the history, and we just got done talking about two case studies about transformer oil and adhesives. And then the third part we really excited about is how can we get some laboratory experiments on soybean oil into the labs, right? To teach those hands-on skills, but also use the material that students might want to use. There. So one of the things we're doing is we're actually working on epoxidizing this soybean oil. And while it's readily available, one of the interesting things we want to do is, can we do this epoxidation with a green oxidant? And that green oxidant we chose was oxone. And we were able to apply a procedure that was done from the Dean Webster Group at North Dakota State. Again, a person that had been funded by the US Soybean Board. And we were able to actually get this done. Jane? So there's the curing cross-linking. That's kind of the second step we're going to do. If Jane hits the second thing. Just to tell you a little bit more, oxone's a green oxidant. This is easily for students to weigh out and mass out. It's wildly inexpensive. We don't need any extra catalyst with this system, and we can use water as a solvent. The product is biodegradable, and there's no volatile organic chemistry released. And then what we plan to do from this first step is then use this to make the adhesives, right? So if you go back to think, we have the epoxidized soybean oil. So we've added that functional group that has more reactivity. Now we can add some renewable cross-linkers, and we can actually turn these materials into adhesives and composites. So here's a picture of this. So I could barely believe this, but I purchased soybean oil from a large place in Minneapolis. You can guess where it was from, perhaps. And I couldn't believe we took an NMR of this material, and it's just a beautiful, clean NMR. And it's really fun for students to see this. There's a lot of functionality going on. But if you really kind of hone in on those vanillic HAs, those blue starred peaks right there, that kind of shows you that vinyl group that we're kind of looking at to functionalize along the way. So it's a nice, clean NMR system for students to learn and adapt these kind of things as well. And so then we go ahead and epoxidize this. And as you can see, there's a shift. The red now, we have these epoxides are now in place. And you can see the shift there as well, and the disappearance of the vinyl hydrogens from before. And again, we've got this to work in a system in under about an hour. So we're always thinking practically as well. This needs to be done in a 3 to 4 hour lab time. And so we can get this done already in a really short amount of time with, again, a green oxidant, highly renewable feedstock, and we're making this new clean, really clean, and easily purifiable epoxide soybean oil. And then from there, now we get to the fun part. We haven't quite got this figured out, but you can see from the picture that's a sticky material. That's no longer an oil. That's an adhesive of some level. And we've tried cross-linking this with different types of natural acids with different numbers of carboxylic acid functionalities. So there's some interesting things for students to think about stoichiometry wise as well. And we haven't quite figured this out yet, to be pretty honest, but we're working on this. And this is kind of the next thing. Once we kind of get this going, we'll hopefully see some different properties that we can measure as well. And we actually are trying with, they're the acids. So you can kind of see the different types that we're working with, again, all natural acids. And hopefully we'll see some different structure and function with these different acids as they are obviously different cross-linkers. Maybe we'll get different adhesive properties as well. So to summarize, right? You know, I am a small town Iowa boy at my heart, and so this is kind of, I always think this is kind of a neat full circle moment. I have a younger brother that works in agricultural business, and this is kind of a fun thing for me to be a part of, that grew up at a small town hardware store in Iowa. And so we have this three-pronged approach to kind of bring this to students, bring this to our educators. The first part is modules about the history and this idea of where it all came from, some of these physical properties. The second part, we have these interesting case studies that are highlighting, you know, classical uses, cutting edge uses, to really kind of bring to life some of the things we're already teaching, these concepts we're teaching in classes, but giving them really interesting context that focus on sustainability and renewable sources. And then finally, this last module was developing these new labs that really show the uses and show how easy some of this chemistry is, but also by applying some green reaction methods, highlighting those sustainable development goals and all those things along the way. And so that's what we're working on. So finally, I mean, I can't help myself, but from lipase to lecithin, these little legumes are soylent evidence that chemistry is everywhere. And we'd of course be happy to take any questions as well.